Okay, so be careful what you say. All right, so has to be politically correct. All right, so this is just kind of for educational purpose. Since some of you are not from this background, I'm just going to show how we do total energy calculations. This is such an important quantity, right? So anyway, so let's start from many body electron problems that with Born-Oppenheimer approximation. So the wave functions for any electrons satisfy this many body Schrödinger equation. That's all, we all know that. So where there's an electron-electron interaction term and the electron with external means are ionic potentials. Where we use these atomic units, where h bar is 1, mass of electrons is 1/2, and the e square is 2. So remember, 2 will appear somewhere down the road. It's because of e square. Just keep that in mind. Where external potential is given by this 2 here is purely because of e square. And electron density is given by this expression. It's no doubt about it. S is stands for spin. And I pick up this electron to calculate electron density. It doesn't matter because it's all identical particles. Right? You can exchange electrons. All you change is sign of the wave function. So that you can just use this coordinates for determining the electron density. So that's kind of definition. And then so spin up, spin down give the total electron densities. So that's all we how calculate electron density. And total energy is given by this electronic total energy is given by this, right? So it's in the framework of many body theory. This is how, in principle, this is how we can do it. The total energy of the solid, we just have to add this term, electrostatic potential term, because of ionic energy. And there's of course, this kind of a double counting here. So you have to do 1/2, but seeing as because e square has 2, so it's all 1/2 and 2 is cancelled. So that's why you get this. Okay. All right. So in reality, we have to do we have to calculate this energy in the previous slide from in the framework of DFT. So that's how the way we do that is by in a DFT, as ground state, electronic total energy E is a function of electron density rho. So given by this expression, where the rho can be calculated using this formula. So this is a kind of fictitious one electron wave function, which is called Kongshan orbitals. So of course, once you calculate it for spin up and spin down separately, you add them up is total electron density. Right? So where the F is the Fermi-Dirac function, then this is given by this expression for temperature T, where the a single particle wave function satisfies so-called Kongshan equation, right? It has to be the self-consistent solution of this expression. Then they have this 3 different terms. One is Hartree potential, this external potential, which is shown in the previous slide, and exchange correlation potentials. The alpha itself just symbols the so-called Kongshan orbitals, which can be, if for periodic system, you have K vector and also you have a band index. So alpha stands for all those combination of that. Where the Hartree potential is given by this. Then there's a exchange correlation potential. Of course, this only exchange correlation potential is a spin dependent. The Hartree and the external potential doesn't depend on spin. Just keep that in mind. Where the external it's just from it's copied from the previous slide. So so the many body problem becomes a one electron problem with the effective potential given by this, right? So just treat this as effective potential. So this will become one electron problem. By solving this self-consistently, you can determine rho electron density instead of from a many body theory, but now you can get it from a single electron theory. You can calculate total energy this way, okay, instead of doing many body theories. All right, so this part is an effect of it's a Coulomb potential. Okay, essentially it's a Coulomb potential. All right, so now we can consider we decompose the electron total energy. Let's take a look each term. So the kinetic energy term, how we calculate it. So this kinetic energy term is essentially, it's not surprising. is calculated this way, based on DFT, that you sum over spin and also you sum over all the orbitals, and you calculate, you just operate on this kinetic energy operator, calculate average. Of course, if you use the plane wave basis, you can always expand this Khongqian orbital or Bloch wave, right? In terms of like plane waves, then you can just operate this on the plane wave. You can easily calculate. But if we do not use a plane wave as basis, like in KKR, so this kind of operation is not difficult. It's not easy. But seeing as we use a Khongqian equation, we replace that by this expression, right? This is just based on Khongqian equations. So we can just write things like this. Then you just break that into two terms. Remember that you have what you can do is I can write these things as an integration over the epsilon. We put a delta function here, right? I'm not breaking the algebra. All I have to do, I just replace this delta function. Okay, you see that? The second term is here. All right, so this is just kind of rearrange the algebra. So the remember that, keep that in mind. Rho, this is kind of electron density. Okay, as this is just from a previous slide, right? Because that's how electron density is constructed in DFT. Okay, so I can rewrite these things by using, just replace this part by this rho, and then this part, it was in parentheses. Actually, it's just density of states. Okay. All right. So I can just write things like this. Right. So that means total kinetic energy term is basically just a density of states multiplied by epsilon, integrated, and minus this part. Right. So it's the Coulomb, then the Coulomb energy term is given by this. Right. This is based on the DFT. So this is a Coulomb energy term, and then the exchange correlation energy term is using this local density approximation. Basically, it's given by this expression. So all we have to do, we have to get it from somewhere else, this epsilon xc, right? Once we have that, fortunately, there's a libxc library being built by quantum chemists for us to use. We can just use that library to get this epsilon xc's from them. So all we have to do for us to worry about is to solve the to calculate the rho and calculate total energies. Right? So this is how we break down the total energy. This is how we calculate in principle. Okay, so then we'll take a look at the electrostatic potential and band energy. Again, for the effective potential, it's given by this, right? So just copy over from the previous slide. The sum of first two terms is the electrostatic potential. This is the Hartree potential. This is the external potential. External potential is from all the ions, and Hartree part is from the other electrons, electrostatic. Okay, basically I just write down things like this. Again, 2 is because of E squared, right? So it's there. So there's a Coulomb potential, whose calculation will be this. We can talk about it from sometime in the future, because that part is the one we saw this linear relations, QBs. So we need to talk about how we really calculate it, because this seems like a difficult problem, because this sum over the entire space for the ions and the integration over the entire space. We have to kind of really reduce, figure out a way to do this calculation. But anyway, in principle, this is given by this. So the effective potential basically is the Coulomb potential plus exchange correlation potential. Again, Coulomb potential is a spin independent. The exchange correlation part is a spin dependent. Right? Keep that in mind. Oh, you can stop me if you want. Have any questions, right? So at t equals 0, the first electronic total energy sum becomes. Remember that in the previous slide, when we calculate total energy, the first term is given by this. We have integration over for the entire energy. So at t equals 0, of course, Fermi Dirac become a step function, and it's just given by this expression. Okay. Usually we do t equals 0 calculate, but of course you can introduce finite t. But t, this is for the electronic temperature, right? So if you apply the adiabatic consideration, the T is only for electronic systems. You may have different T for ions. Anyway, so for T equals 0, you have this, right? Then you can also break down further that for all electron methods, we have core states and the valence states. The reason we make this as a distinction because we apply different techniques to solve the core states and the valence state, because core states are bound states. Their wave function become just decay to 0 at infinity, right? So we can apply this kind of boundary condition to solve the core states by solving the differential equation. On the other hand, for the valence, they have they are block waves, so the wave function do not become 0 at infinity. So you don't have that kind of boundary conditions. You have a block wave boundary conditions. So it's different. So the technique is different. So we can break this down into two different terms. One is for the core states, another is for the valence. So this integration is from the bottom of the valence band to the Fermi energy, and anything below will be the bound states or the core states. We can calculate exactly by solving the Khongshan equation with proper boundary conditions. So this easy can be calculated. So that's why we sum over here. This is in practical. That's how we do it, right? We solve core states and valence states with differently.
I have a question. When you calculate the core states energies, how much does it depend on the, say, on the volume of the crystal or the distance between atoms? I mean, most naively, you would think that when the distance became large, it reduces to the atomic limit, and then you bring them together. There's a correction. How big is this correction to the atomic?
In practice, what we usually done is we have each atom has like a fixed size cell around each atom. We put like a bounding sphere. That's the radius we use. We consider that the wave function will become like a Hankel functions. The Hankel function will go to infinity. When it got infinity, Hankel function becomes 0. Right. So the bounding condition satisfies. So basically, we use the atomic bounding fixed size cell bounding sphere as the as consider that the potential is becomes 0 because locally we're solving this for the bound states. So we assume that the boundary condition is become a Hankel function at the bounding sphere. We apply that boundary condition to calculate the core state.
I want to know if I just use the atomic values for EC.
Oh no, you cannot. Well, the potential itself is affected by your self-consistent calculations. Each iteration you have to update your potential.
So you're saying there's a substantial correction with respect to
yeah. The potential itself is still. We solve this EC, the core energy, using the effective potential.
Right.
Using this effective potential. So that that's just self-consistent. That update itself each iteration. So you cannot just pick up atomic values. You can't do that.
Right. Well, I could imagine that the correction due to this is big or that it's very small, and so I just don't know. And I'm asking. So you're saying that this correction, it's a bad approximation to use atomic energies for core states.
That's right.
So for very deep core states, it's probably wouldn't be too bad of an approximation. And that's also why in chemistry you can do things like the frozen core approximation, where you just calculate all the deep lying core states once and never recalculate them ever again.
Yeah, for those shallow core states, certainly it's going to be affected by. Remember, there's a colon not only from the itself, but also from all the crystal environment. It's all being included in the effective potential. So that's right. For deep core, I believe that's pretty much will not change because it's dominated by Z over R. Of course, there are terms involving other it's a crystal field. So we have to calculate each iteration. But fortunately, this calculation is very easy. It takes no time. Compared to calculate band structures, this part, this is nothing. So,
Okay, I see.
yeah, it's kind of insignificant to solve this, right? So that part is not difficult. So we have
yeah, in this slide, the last expression, right, where you have integration epsilon ft, right? So at t equal to 0, the Fermi-Dirac function is just a step function. Just to clarify.
You mean this expression?
Yeah, this expression.
I assume t equals 0.
Yeah, so it's just a step function. So it's either going to be 0 or 1 exactly.
Correct. Yes.
Yeah,
Okay.
that's a Fermi-Dirac. Yeah, that's right. You know the Fermi-Dirac, right? That t equals 0, then this f will become 1 below Fermi energy, with 0 become.
Okay, so why don't we just choose until the Fermi energy? Like, why do we need to write it like this? So why do we have an infinity there and not just integration from 0?
Okay. Yeah, in principle, you can write. Yeah. It just if temperature is finite, in principle, you should integrate to up to infinity, because some electronic states will at finite temperatures could be occupied. I'm not sure if I understand your question. Why I write this way? But usually you see things like this because we only consider temperature equals 0.
Yeah. So my question is, like, can you extend this to finite temperature, or it's
this is finite. Yeah, finite temperature is like this, right? Okay. So basically, you have the EC. Then this is from EB to infinite with a f. There's a Fermi-Dirac function here.
Okay. Got it.
But in practice, of course, you cannot just integrate up to the infinity, right? In practice, you can do that with you can expand f in terms of that Maspera pose. That's another way to do it. So you sum over Maspera pose.
Okay.
Yeah, but
Thanks.
that's a different topic. It's just formally you just can write things like this. But temperature equals 0, you get a term. You only integrate up to the Fermi energy. Okay. So so whose density of states is basically a delta function. That's why it just become a discrete summation. Okay, so EB is the bottom of the valence band energy, and rho v is the density of the valence states. Right. So basically, that tells us the answers how we consider this is called band energy. This term is recognized as called band energy. That's by tight bonding physics. For people who deal with tight bonding method, they always call this band energy. Okay. All right. So for the electronic static energy of solids, so electrostatic energy is basically this U, and where the external potential is given by this. So I just copied over from a previous slide. Now, of the solid, you just have to add this term to it. So not only the electronic part, but also ion interactions need to be added to this. So you just add this term, okay? Then what do we do next is I just regroup things. I just break this term. This electron ion interaction term. You remember there's a 2 here. The reason there's 2 here because E squared, right? So I just break this term, just break that apart. So one will be grouped into this part, another part will group into this part. Okay, so basically that's just you can just this 3 terms can be written as this this expression, just kind of regroup. Okay.
So one point to note here is that there is if you just write it like this, there's a problem with the rho prime, because it basically contains a repulsion of an electron from itself.
Yeah.
That there is a self-interaction error that hopefully gets
that's not
by exchange correlation.
Yeah, that's DFT in principle should be taken care of in DFT, but when we apply local density approximation, that part the 7 correction term is not properly done in the But anyway, that's
if I can just mention this, we were doing a calculation on the lattice of hydrogen atoms with LDA plus DMFT, and it turns out, so when the atoms are very far from each other, you can ask, does LDA code recover the binding energy of hydrogen? And instead of getting 13.6, you get 6 electron volts, and that's because of this reason. There is a self interaction. I mean, the hydrogen has only 1 electron, which cannot interact with itself.
That's a very famous problem. Yeah, that's right.
Yeah, so that's what happens, and you can't, you have to live with it.
Yeah. Anyway, all right. So this the electrostatic energy of the solid can be written in this way. All right. Then we define, obviously, this what's in the bracket is a Coulomb energy. We defined previously is a Hartree term plus the external interaction term. So basically, it's a Coulomb energy in solid. So we can replace that by this expression. Okay. All right. So that's how we kind of evaluate each terms in the total energy expression. T, the kinetic energy term, the U term. So we just kind of rearrange the terms. So finally, we get something that is practically can be implemented. So this becomes this expression. Okay. So finally, we come to the so the conclusion is the effective potential can be written as Coulomb potential plus exchange correlation potential, right? So that's the first thing we recognize, where Coulomb potential is the Hartree term plus external potential energy term. Then we also recognize that kinetic energy term can be written this way, right? So that's what we have written in the two slides previously. And then this the total electrostatic energy term of the solid is U plus this one can be written as this, right, from a previous slide. So now the total energy of the solid is actually what we calculate. It's not the total energy of the electron itself, but total energy of solid is therefore given by this, because this is an ionic interaction term, and given by this, right? So this is how we calculate. So thing is, we need to calculate the rho, the density states. We calculate this band energy. I guess
I mean, between each iteration, you're in DFT, you have to calculate the density, right? And then you also have to calculate the eigenvalues, right? So how do you solve for the kinetic energy if you have two unknowns?
Oh,
right.
That's right. Okay. So basically, you worry about how we calculate this?
Yeah, right. Because at every step, you're recalculating both the density and the energy.
I'll share how we calculate this, right? So the thing is how to calculate rho and how we calculate the band energy. Okay, I'll my next slide, right? All right. So anyway, so we have this part. Of course, this part includes the core state energy plus the valence band energies. And this term that if we can calculate the Coulomb potential, all we have to do is multiply the charge density, or the Coulomb potential multiplied by the z's. We add them together, and this part is just the exchange correlation part. This is spin dependent, so I have to calculate spins. I calculate charge density for different spins. So this is just exchange correlation energy terms. So all add this together will be the total energy of the solid. This is how we do the calculation, formally, in principle. Okay, so basically this part, as I mentioned, which is break that into core state energy term and the valence is called a band energy term. And so this part, as David just asking how we calculate the rhos and epsilons. There's different techniques to do that. For Green's function method, we have very much advantage for doing this. For band structure, you can do that in the band structure calculation. That is, you solve each band structures, but they may use different techniques for do these calculations. But what I'm going to show is how we do that in KKR. Okay, all right. So that brings it up into the Green's function technique. So consider electron density given by this. All right, I just copied over from the original slide. That's how the electron density in the DFT is constructed by a Komshan-Elberthal square, right? I just multiply by the Fermi-Dirac functions here, right? In general, this of course we usually think about, we're only interested in temperature equals 0, then the summation will be over up to Fermi energy when it's sum over. Okay, but formally you can write things like this. Okay, so then what I do is next is I'll just put a delta function here. Okay, I'm not breaking the algebra, or I rewrite these things. I just write I integrate epsilons so that I should replace epsilon alpha s by epsilon self, because I put a delta function. Okay, it formally can be done this way, right? Then I just take that integration out of this, put a summation inside. This is how I can write things like this. Okay, so why I do this? Now, I use this fact. This complex analysis. This 1 over z plus eta. I let eta approach 0. It can, because of complex function, it basically get can be written down in the two terms. One is called a principal value term. It's 1 over z minus I pi delta function. Okay, this is just simple a complex function. This is just simple fact. I just quote here. So I use this relation. Basically, the imaginary part of that means the imaginary part of this guy is just pi delta function. Okay. So we have this part. I just replace that by I just replace delta function by this expression. Okay. Right. I just replaced a delta function. So I just look at this, what's in this bracket. I replace delta function by this expression. I just using this simple complex function fact. Okay, I do this. And then I recognize that because this is called a Green's function. Okay, because of that, this can be written in terms of Green's function. All right. So basically, what's inside this bracket is the imaginary part of the Green's function. So therefore, in terms of Green's function, the electron density can be written like this. All right. So at temperature equals 0, you get this. All right. Why I do things like that? Because in KKR, we can calculate Green's function easily. By the way, S here, S means a spin. Okay, I calculate a Green's function for each spin channel. So that's got S index here again. All right. So I write things like this because in KKR we have KKR is in the multiple scattering theory, we can calculate Green's function. That's why KKR also called Green's function method, because we can calculate Green's function easily. All right. So once we calculate Green's function, we can find the electron density this way. All right. How about density states? For density states, this density states we defined from 2 or 3 slides ago, right? So we do the same thing. We just I take the integration outside and put the summation inside, then apply the relation shown in the previous slide. This can be, you can easily, that's what we have, right, from a previous slide in terms of the imaginary part of the Green's function. So that we have that density of states is the imaginary part of the Green's function again, but integrating over the volume. Okay. Also, we can, because this integration over the volume, we can integrate over the atomic volume and sum up for all the atomic volumes. Okay. So we can certainly define this to be the density states in the local volume. Okay. So nice thing about this KKR method that we can calculate Green's function, we calculate density states, local density of states, so conveniently for us. All right. So back to David's question: how do you calculate the band energies? That's how we calculate band energies. Is we calculate the density of states for each atomic volume, and we sum them up. That's for the entire unit cell, we calculate density states for the entire unit cell. We multiply that by epsilon, then integrate from the bottom of the band to the Fermi energy. That's how we get the band energy, which is the first term in the total energy term. Okay, that's how we calculate. We don't really do the band structure calculations. We calculate Green functions. Then contour integration. Then why we do the contour integration? Because when we integrate the energies, you may choose to go along the energy axis, but we take advantage of the fact that the Green function itself is as an analytic function, so that we can take a contour integration, because we need to calculate this integration, or we just break that down into, as I mentioned that, we calculate the electron density can be calculated as sum over the core electron densities and the valence electron densities, right? So core electron density are calculated separately using different technique, as I mentioned that, which is solve the Komsian equation for the bound states. We calculate electron density using based on the fact that they're bound states. Then add the electron density for the valence, which using Green function technique. So in this, when you break down like this, the energy integration is from the bottom of the band to the Fermi energy. Okay, CS is the electron density for the core state C with spin S, right? Then this integration, I can, from the bottom of the band to the Fermi energy, I can choose to go along the real energy axis, or I can go like a contour. The reason I want to do that, because in the complex energy plane, the Green function become very smooth, easy to integrate. So I don't have to choose many grid points to do the calculation. So I can choose you can use like different numerical techniques. End up you use like a tens of points will be sufficient to do this integration. Okay, so it becomes much easier to do this integration in the complex energy plane. So the band energy calculation is running this way. That you can have by using the fact that density states is given by this expression from a previous slide. So you can, all you have to do is you just write down things like this. Then again, we do a contour integration here. To replace epsilon by z, we do integration over the energy complex energy plane. So that's how we calculate band energy calculations. So I think that will answer David's question. Okay, in practice, that's how we do it. We calculate the things in the complex energy plane. First thing, we calculate electron density by doing integration in the complex energy plane, and for the band energy, we'll also do that in the complex energy plane. Okay, but essentially, what means that we calculate a Green function in the complex energy plane. So that will help us to calculate both electron density and the band energies. That's how it's done in the KKR technique. Yeah, I think that's all I want to say. That's basically summarize what we do in the KKR. Any questions? Okay, then I stop share. I will stop recording.